You're listening to Scientific Giants Who Changed the World. Each episode stands beside one mind and follows a thread of curiosity until it ties to the world we inhabit. Today, we enter an operating room where the patient is awake, the skull is open, the brain is exposed, silent, pale, almost unreal, and yet it contains everything the patient has ever been: childhood, language, fear, music, memory. A surgeon touches a tiny point on the cortex with a mild electrical current, and the patient suddenly speaks a sentence from decades ago, smells something long forgotten, or feels a hand move without choosing it. This is not science fiction, it was clinical practice, and the man who turned this practice into a map of the mind was Wilder Penfield. Wilder Graves Penfield was born in 1891 in Spokane, Washington, and grew up with a kind of disciplined intensity that would later make him both a careful surgeon and a bold thinker. He trained in medicine and surgery at a time when neurosurgery was still young and frightening. Operating on the brain meant stepping into unknown territory with limited tools and enormous risk. Yet Penfield was drawn to it, not because he enjoyed danger, but because he believed that the brain, if approached carefully, could be understood. He trained broadly, traveling through major centers of neurological science. He learned from surgeons and neurologists who were shaping early brain medicine. Over time, he developed a central mission: to treat epilepsy. Severe epilepsy can destroy lives. Seizures can be violent and unpredictable. In some cases, medication fails. In the early 20th century, many patients with epilepsy were stigmatized, institutionalized, or treated as hopeless. Penfield believed they deserved something better: a surgical approach grounded in careful localization, finding the exact region where seizures begin and removing it while preserving function. This goal forced a problem that goes straight to the heart of neuroscience. Where exactly do functions live in the brain? Where is movement? Where is speech? Where is sensation? Where is memory? To answer those questions, Penfield developed and refined a surgical method that required patients to be awake during parts of the operation. The reason is both practical and astonishing. The brain itself has no pain receptors. You can cut skin and skull under anesthesia and local numbing, but once the cortex is exposed, stimulation can occur without pain, if done properly. This makes it possible to ask the patient questions during surgery. It makes it possible to test. Penfield's procedure, sometimes known as the Montreal procedure, became famous because it merged surgery with experimental mapping. During surgery, Penfield would apply mild electrical stimulation to small areas of the cortex. If a region controlled movement, stimulation might cause a hand to twitch, a leg to move, a face to grimace. If a region processed sensation, the patient might report tingling, warmth, pressure, or a strange feeling in a specific part of the body. Penfield carefully recorded these reports. The brain began to reveal itself not as an undifferentiated mass, but as a functional landscape. One of Penfield's most iconic contributions is the cortical homunculus, a distorted little human mapped onto the brain's surface, showing how different body parts are represented in motor and sensory cortex. Hands and lips appear huge because they require fine motor control and rich sensory input. The trunk appears smaller. This homunculus is not a joke or a cartoon. It is a visual summary of how the brain allocates space to the body. It is one of the clearest demonstrations that the brain is not built in proportion to physical size, but in proportion to control and sensitivity. But Penfield's work did not stop at mapping movement and sensation. The deeper drama came when he stimulated regions associated with memory and experience, particularly parts of the temporal lobe. In some patients, stimulation triggered vivid experiences: hearing music, hearing voices, reliving scenes, smelling odors, feeling as if they were back in a specific moment of their lives. These were not vague emotions. Patients sometimes described them with precise detail, as if a recording had been played inside their consciousness. Penfield was struck by this. It suggested that memory might be stored in a way that could be accessed by direct physical stimulation. This led to controversial interpretations. Penfield sometimes spoke as if the brain contained recorded tapes of experience, and that stimulation could play them. He did not mean this metaphor literally, but he was trying to express something real. Memory is not an abstract cloud floating above the brain. It is embedded in tissue. It can be evoked. It has a physical address, or at least physical pathways that can be activated. Yet the story is not simple. Not every patient had these experiences. Some reports may have involved imagination shaped by suggestion. Some may have involved fragments rather than complete memories. Modern neuroscience views Penfield's memory findings with both admiration and caution. But even with caution, the core achievement remains. Penfield demonstrated, in living human brains, that stimulation of specific regions can produce specific experiences. He made the mind experimentally approachable in real time. What made this possible was not only Penfield's technique, but his ethics and care. Awake brain surgery is an intimate encounter with personhood. The patient is not a passive body. The patient is present. The surgeon must treat them not as an object, but as a collaborator. Penfield's success depended on trust and on his ability to remain calm while navigating one of the most delicate environments imaginable. Penfield also built institutions. He helped found the Montreal Neurological Institute in Canada, creating a center where neurosurgery, neurology, research, and patient care could work together. This kind of integration seems normal now. He understood that to treat brain disorders effectively, you needed not only surgeons, but scientists, not only technique, but theory. His work changed epilepsy treatment. By localizing seizure foci and removing them when safe, he gave many patients their lives back. He also helped establish the practice of functional mapping, now common in neurosurgery. Surgeons today still use stimulation mapping to avoid damaging essential functions when removing tumors or epileptic tissue. Penfield's methods became part of the standard toolkit, not as a museum relic, but as a living practice. Penfield's influence also shaped how the public imagines the brain. The idea that touching a spot could move a finger or evoke a song made the brain seem both mechanical and mysterious. It raised questions that remain unresolved. If stimulation can trigger action, what is free will? If stimulation can evoke memory, where does identity live? Are we simply the sum of circuits? Penfield himself wrestled with these questions and did not reduce the human mind to mere machinery. He saw the brain as necessary, but suspected consciousness had qualities not easily captured by electrical maps. Whether one agrees with him or not, his humility matters. He did not confuse his map with the territory. So how should we remember Wilder Penfield? We should remember him as the man who turned the living human brain into a mappable landscape. Not in a crude or dehumanizing way, but in a way that saved lives and expanded understanding. He proved that function can be localized, that sensation and movement have cortical geography, and that the brain can be explored with careful stimulation while a person speaks back. His work sits at a strange intersection of precision and awe, the brain as tissue you can touch, and the mind as experience you can never fully reduce. We should remember, too, the courage of his patients, people who agreed to remain awake, to answer questions, to report sensations and memories while their brains were exposed. Their participation turned surgery into science and suffering into insight. Penfield's legacy belongs partly to them. If you want a final image, picture the operating room quiet, except for voices. Picture Penfield leaning over the cortex with a stimulation probe, applying a tiny pulse. Picture the patient suddenly saying with surprise, "I hear music," or "My hand moves," or "I'm back in my childhood kitchen." Picture Penfield marking the spot carefully, not as a magician, but as a cartographer mapping a continent that is also a self. You have been listening to Scientific Giants Who Changed the World. Today we followed Wilder Penfield from epilepsy surgery to cortical mapping, from homunculus to memories sparked by stimulation, from brain as mystery to brain as landscape. In our next episode, we will meet Eric Kandel, who took the problem of memory into a sea snail and showed that learning leaves physical traces at synapses, turning remembering into something you could track in a circuit. Until then, thank you for your attention and your time. This episode was written as a continuous story for the ear, because Penfield's work is not merely a medical technique. It is a human encounter with the brain's geography, a reminder that within a few millimeters of tissue lies the difference between silence and speech, between motion and paralysis, between the present moment and a memory you didn't know you still had.